This is a lecture on examples of the section 5-3, and we're going to start with example 5-15 on page 276. I highly recommend opening a book to that page so you can read with me. This example on deciding whether each experiment is a binomial experiment. If it's not, state the reason why. So as I said, the hardest thing about binomial distribution is recognizing it. So this is why it's a separate example. So let's take a look at part A. Selecting 20 university students and recording their class rank. So if I'm selecting 20 university students, that's my n is equal to 20. That's great. And recording their class rank. Now, is their class rank yes or no? And the answer is that cannot happen because a class rank is your freshman, sophomore, junior, senior, or maybe a graduate student. So you cannot boil this down to yes or no question. So the answer to part A is no. 5 possible outcomes. Part B. Selecting 20 students from the university and recording their gender. Okay, so this is where you have n is equal to 20. And possible outcomes. Are either male or female, so there's only 2. So the answer is yes, this is a binomial experiment. Drawing 5 cards from a deck without replacing and recording their whether they're red or black. So this is part C. I am recording red or black, but I am taking 5 cards from a deck without replacing. If I'm without replacing, what I have is the probability is not independent. Because the probability of choosing a second card depends on what I have chosen for the first card. So the answer is no, not binomial. Even though we are talking about red versus black, still not a binomial. Selecting 5 students from a large school and asking them if they are on the dean's list. Okay, I have selected 5 students. I asked a question. The question has either yes or no answer. So this is a yes binomial probability binomial experiment. Part E. Recording the number of children in 50 random selected families. So my n is 50. And what I'm trying to record is number of children. Now, number of children is not a yes or no question. You could have 0, 1, 2, 3, 4, 5, and I don't know, 12. So no, not binomial. Now in part E, you can actually rephrase this. Ask 50 families whether or not they have children. So do you have children? Yes or no? Next family, do you have children? Yes or no? Or maybe you want to subdivide it into 0 or 1 kid versus, more than or 2 or more. So it's up to you how you want to phrase this, but as written in part E, this is not a binomial experiment. So what I want to do right now is look at this formula for a binomial probability formula. So the probability of exactly X successes in N trials. In N trials is given by, so the probability of X successes in N trials. You're going to take that N factorial divided by N minus X factorial that, X factorial, so that's your choosing numbers, that N choose X. Then you're going to multiply the probability of success, raise it to the power of X, and multiply this by probability of failure, N minus X. The algebra of this formula is discussed in great details, usually in an algebra course. What I'm hoping for this semester is that you use a calculator. Now, I will guide you through this formula at least once, so you want to try this at home at least once. But by the time the test comes around, this should be done fairly quickly with a push of a few buttons. So let me show you how the formula works first. I am on example 5-17. A survey found that 1 out of 5 Americans say he or she has visited a doctor in any given month. If 10 people are selected at random, find the probability that exactly 3 will have visited a doctor last month. So what I need to be able to do is going back to that notation. The notation is P, Q, N, and X. I need to find those P, Q, and X. I should be able to find those in a sentence and be able to write those down. So what I'm going to do is I'm going to read the problem again. A survey found that 1 out of 5 Americans say that he or she has visited a doctor. So visiting a doctor is what my experiment, that's my event. Does it have 2 outcomes? Yes, you either visited or you haven't. So what we went is we conducted a survey and we found out that 1 out of 5 said yes to my question. So that's the probability of success. My survey showed that 1 out of 5 answered yes to whatever my question was. That means that right away I can find Q. That's 1 minus. Remember, Q is always 1 minus P. So in this case, it's 4 out of 5. I'm going to continue reading. My problem. If 10 people are selected at random, so that's my N, find the probability that exactly 3 will have visited a doctor. So that's what I'm looking for. That's my X. So the probability of X, I have the formula right up there. So the probability of getting exactly 3 successes in N trials is 10 factorial divided by 10 minus 3, 7 factorial, 3 factorial, times, you're going to take your probability of success, raise it to the power of X, which is a 3, times the probability of failure, raise it to the power of N minus X, so the other 7. So this is how you want to read. Yeah, this is called the binomial coefficient. It's the choosing numbers, and then you have your probability success, your success. So you have 3 successes, therefore you have 7 failures. So those probabilities are shown as the power. You can kind of backtrack it to something that makes sense in chapter 4, if it actually made sense in chapter 4. So what you're going to do is you're going to try to do this in a calculator. You should be getting 0.201. So the book has 3 significant digits. I tend to ask for 4. So make sure to give me at least 3. And what we can do is we can do the next example. My next example is 5-20. And I will do exactly the same thing. A public opinion reported that 5% of Americans are afraid of being alone in the house at night. So, afraid of being alone in the house at night. That's my event. This is what I'm going to call success. Finding the people that are afraid of being alone in the house at night. So, I'm going to start reading it again. A public opinion reported that 5% of Americans are afraid of being alone in the house at night. So they just gave me a probability of success. If a random sample of 20 Americans is selected, find the probabilities by using the probability table, which we're not covering in this class. So find the following probabilities. I'm going to read that sentence again. If a random sample of 20 Americans is selected, so they gave me n is equal to 20. Once they gave me the p, automatically I know what q. If 5% is probability of success, the other 95% is the probability of failure. Please make sure to write down all of your probabilities as 0 point something. Now the x's are coming in part A, B, and C. Find the probability. Part A. Find the probability that exactly 5 people in the sample who are afraid of being alone at night. So they will repeat this phrase of the success, quote unquote, afraid of being alone in the house at night, every single time they're going to ask you a question. So part A says find the probability that there is exactly 5 people in the sample. So they asked us the probability, so they told us x is equal to 5, and they're looking for the probability of exactly 5 successes in n trials, in 20 trials. So if you'd like, you can put this into a formula. But what we're going to do is I will actually finish this example on the next video with a calculator. So if you use the calculator, you should be getting this number, and we'll get back to this on the next video. I do want to give you a setup for part B and C before moving on. So part B is there's at most 3 people in a sample who are afraid of being alone in the night. So what I need to do is I need to show you the distribution, except I'm not giving you the whole distribution. I'm just giving you the x-axis, meaning I could either have 0 people in the sample that are afraid of being alone. Is this possible? Yes, very unlikely, but possible. Can I find, or 0 is actually fairly likely. The 20 is unlikely, because if the probability of success is only 5%, if I select 20 people and all of them are afraid of being alone at night, that's unlikely. So, because this is a binomial distribution, it is a discrete distribution, so there is nothing between 3 and 4. And there's nothing between any of the 2 consecutive integers. So what I have is, I'll label it like this. And in part B, they're saying at most 3 people. So they want the 3 people, but this is at most. So what you're doing is you need to add the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3. I'll show you how to do this on a calculator. And the probability of getting at most 3 is written like this. X is less than or equal to 3. and we should be getting 0.984. And let me show you last part setup. There's at least 3 people in a sample. So what I'm doing is I'm drawing exactly the same one. I know there's 0, 1, 2, 3, 4, 5, 6, all the way up to 20. So, and now they're saying that I want at least 3 people. So I want 3 or more. I want 3 or more. So adding all of these numbers up. So in order for me to find this probability of at least 3, you can either look at this like we did in the previous example, where it's 1 minus the probability of 0, 1, 2. I need those parentheses. Or you can look at this as the sum of the probability of 3 all the way through probability of 20. As you can see, this is a cumbersome process, especially if you think of each of those is a formula as this formula, the binomial probability formula. Each one you have, each x that you have right here, the 0, the 1, the 2. Here you only need to use formula 3 times and then 1 minus. This time you need to use the formula 18 times. Not fun. So both of these you will be able to do in a calculator, but the answer for this one is 0.076 according to the book, and we will look at those as a calculator problem on the next video.